an interstellar object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond.
On a clear night in July, a streak cut across the dark like a silver ribbon. Backyard observers could see it through small scopes. It slipped slowly, deliberately, a long, thin smear against the stars. The question that followed was simple and terrifying. What just came through our solar system? The object has a name now, 3 Atlas. Discovered by the Atlas survey in Chile on July 1st, 2025, it arrived on a path that said one thing loud and clear. It came from outside our solar system. Its orbit is hyperbolic. That means it is not bound to the sun. It is a visitor. The mainstream view is cautious and clear. Most astronomers say it looks like a comet. It behaves like a comet. It sheds dust. It shows water ice signatures. Its tail grows as it warms. But the data also produce a set of wrinkles. Small at first, then larger. Hubble images show an inner glow with an unusually steep brightness drop-off. Spectra from ground telescopes reveal water ice mixed with carbon-rich minerals and silicates. Its trajectory is odd. It approaches the plane where the planets orbit. It tilts only about 5 degrees from the ecliptic. It will pass near Mars on October 3rd, reach perihelion around October 29th, and later sweep past Jupiter's neighborhood. Mainstream explanations begin with dust and ice. Comets are icy dirt balls. As they near the sun, frozen gases sublimate. The gases drag dust away and create a fuzzy coma and a tail. The numbers we measure for 3 Atlas fit that story in many ways. Dust production estimates run from a few kilograms per second up to dozens. Ejection speeds fall in a comet-like range, tens to a couple thousand meters per second, depending on grain size. Those are figures we see in familiar comets inside our system. David Jewett and other comet specialists urge restraint. It looks like a comet, they say. They point to the dust and the plume facing the sun. They remind us that most comets do unusual things the first time we see them. 2 or 3 interstellar visitors don't make a population. Pattern seeking fails on tiny samples. Yet some researchers press an alternative. Avi Loeb and colleagues lay out a paper that reads like a careful experiment rather than a conspiracy.
A supposed comet is catching the attention of some of the nation's most renowned scientists. As one Harvard professor is raising the theory this may actually be a piece of alien technology.
They ask, what if this object is not just a rock or a comet? What if some of the light we see is not reflected sunlight at all, but light the object itself produces? If that were true, the implications flip the scale.
There is just not enough rocky material in interstellar space to provide us with a 20-kilometer rock.
Using standard assumptions that these objects simply reflect sunlight, the observed brightness implies a very large body. Rough estimates put the reflecting body diameter near 20 kilometers. That would make 3I Atlas far larger than prior interstellar visitors, a behemoth. But if the glow is internal, if the object emits its own light, the inferred size collapses. A 20-kilometer reflector could instead be a few hundred meters across if it emitted its own light. That difference changes the statistical probability of encountering such an object by orders of magnitude. Where would self-generated light come from? A few possibilities exist. Radioactive decay in a rock could create a glow. Internal heat could radiate infrared. Or, most provocatively, technology could be producing the light. Loeb and co-authors discuss the power scale. To sustain the observed brightness as internal emission would require energy outputs on the order of gigawatts. 10 gigawatts is the ballpark mentioned, the output of several large power plants. That is a lot for a drifting object to carry for millions of years. Testable hypothesis, they say. That's the key phrase. They do not claim proof. They propose measurements we can make. Look for non-gravitational accelerations. Look for precise changes in trajectory that are not explained by gas jets. Use the Mars flyby. Use space telescopes. Watch how the brightness evolves as it nears the sun. If the glow holds steady in a way that sunlight reflection models can't explain, the anomaly grows. The orbit is part of the puzzle. 3I Atlas is retrograde. It moves opposite the common motion of planets, yet it hugs the ecliptic plane closely. The chance of a random interstellar object arriving with such a small tilt and with close encounters to multiple planets is vanishingly small, Loeb's team argues. They calculate odds like 0.2% for the tilt and something like 1 in 20,000 for the combined close approaches. Those numbers make scientists sit up. Imagine designing a probe that wants to study our planets. You would aim for the plane where the planets lie. You would pass near planets to sample environments or adjust trajectory. You might choose a perihelion that hides part of your maneuver behind the sun. Remarkably, 3i Atlas reaches perihelion when Earth stands on the opposite side of the sun. Observational coverage shrinks. If a craft wanted to conduct maneuvers without Earth-based telescopes watching, the sun makes a convenient curtain. That thought is chilling. It is also speculative. Coincidences happen. Gravitational mechanics is not kind to random trajectories. Many objects will pass through in odd ways. We must not overinterpret a small sample size. Still, the idea is testable. The object's passage near Mars in early October could be decisive. Mars-based assets might get a close-up. The Mars Reconnaissance Orbiter's HiRISE camera could image the visitor as it sweeps by. That would be our best close look without launching a mission. High-resolution images could distinguish an engineering surface from an irregular comet nucleus. They could reveal texture, sharp edges, or unusual reflectance patterns. Or they could reveal nothing but more dust. Either way, the images would be telling. Spectroscopy offers another path. Infrared instruments on space telescopes can map temperature and composition. Early reports show water ice mixed with carbon-rich minerals and silicates. There are hints of CO2 in the coma. Those components are not alien by themselves. Interstellar chemistry can yield strange ratios. Comets from other stars can carry different volatile budgets, formed under different conditions. But here again, the brightness profile is the stubborn clue. Hubble's inner brightness declines much more steeply than in typical comets. The center is disproportionately bright compared to what you'd expect from a diffuse coma. That central concentration could be a compact nucleus, or it could indicate an active, concentrated emission source. Dust scattering can produce steep profiles in certain circumstances. So can camera smearing and image processing artifacts. The community debates these technicalities in honest, detailed terms. Good science looks like that. It tests assumptions. Energy budgets present a blunt check. If internal power were the cause, the numbers escalate. 10 gigawatts sustained over long periods implies either a massive energy reservoir or a very efficient power system. Radioisotope decay can provide steady heat for decades to centuries, as on some spacecraft. But millions of years of interstellar drit at gigawatt levels is a stretch for known physics and materials. That forces us to consider active systems designed to recharge or to use local environments for energy. That moves the conversation from geology into engineering and then into speculation about intent. If 3i Atlas is a probe, the stakes are enormous. We would be staring at evidence that another technological civilization not only exists but has sent hardware across interstellar space. That would change our philosophical and practical priorities. Do you announce immediately? Do you attempt to communicate? Do we study quietly and avoid drawing attention? Those questions carry ethical weight. They also carry real scientific weight. Any claim of artificial origin must meet extraordinary standards of evidence. Most scientists rightly urge caution. NASA spokespeople and many planet hunters emphasize that the simplest explanation remains the most likely, an unusual but natural interstellar comet. They remind us how often nature surprises. They remind us of Oumuamua, which challenged assumptions but ultimately led to new ideas about small body dynamics. They remind us of Borisov, which behaved like an icy visitor from another system. Each case widened the envelope of what comets can do. Still, this story is different in tone and detail. The opportunity to test competing ideas is immediate. The Vera C. Rubin Observatory, soon to come online in force, will discover many more interstellar interlopers. A statistical sample will make rare odds less magical and more mundane. For now, though, 3 Atlas commands attention because it asks questions we can answer this season. Consider practical measurements. If the object accelerates in ways inconsistent with gravity and expected gas outgassing, that would be evidence for active thrust or asymmetric mass loss. Precise astrometry, measuring the object's position against background stars, can reveal tiny deviations. Thermal maps from infrared telescopes can show whether the energy budget fits passive heating or requires an internal source. High-resolution images could show structure. A sudden flare or sustained emission that does not scale with sunlight would tip the balance. We should also watch for chemical signatures that are odd. Isotopic ratios of hydrogen and oxygen in water can show a foreign origin. Some early spectra suggest the water may be isotopically different from typical solar system comets. If confirmed, that is not evidence of technology. It is evidence of foreign formation environments. Still, when isotopic oddities pair with trajectory oddities and a puzzling brightness profile, the pattern demands attention. Public reaction matters. Backyard observers, social feeds, and late-night commentators love a mystery. That can distort nuance. Scientists work in small, that precise steps. They publish measurements, then refine models. Extraordinary claims require extraordinary evidence. The community knows this and behaves accordingly. Yet the human instinct to imagine visitors and probes is powerful. It fuels curiosity. It fuels fear. If 3i Atlas turns out to be natural, the lesson will still be rich. We will learn how interstellar solids form. We will learn about volatile retention in cold, distant environments. We will learn about a parameter space we barely knew existed. It will refine models of planet formation and migration. It will teach us about materials that drift between the stars. If it turns out to be artificial, the lesson will be apocal. The discovery would begin a cascade of questions. Who sent it? When? Why here? How long has it watched? Answers could be scientific, cultural, political. They would reshape our sense of the cosmic neighborhood. They would reframe debates about contact protocols and planetary security. The next months are the test. The Mars flyby in early October is the first real opportunity. If HiRISE snaps useful frames, the public will see more than dots and streaks. JWST and other infrared eyes will measure heat and composition. Ground arrays will track subtle accelerations. The perihelion passage in late October will show whether classic cometary gas emissions ramp up. If they do, the natural explanation grows stronger. If they do not, the puzzle sharpens. There's a haunting aspect to this story. Objects travel on trajectories shaped by gravity and time. They carry histories in their dust and ice. They whisper of formation around other stars. They sometimes carry surprises that push our theories. The universe is not tidy. It is rich with anomalies. We are learning to listen. So what should you watch for? Watch for clear images. Watch for thermal maps that do not match reflected light models. Watch for measured non-gravitational accelerations. Watch how the brightness evolves through perihelion. Watch the Mars encounter. Watch the tone of the scientific papers. Careful, skeptical, methodical. That is where truth grows. In the end, 3i Atlas is a probe only in the speculative sense until it proves otherwise. It is a comet only in the simplest sense until the anomalies refuse that label. What it most strongly is right now is a test of our instruments, a test of our theories, a test of how we handle surprise. Tonight, in suburbs and deserts and observatory domes, people are watching. Small telescopes are trained, software is running, teams are ready to call and share data. The sky, once again, has handed us a puzzle. We will solve it the way scientists always do, by asking careful questions, running precise tests, and letting the evidence decide. What would change if the answer is probe? Everything, and nothing yet. If the answer is natural, we still learn how wild the cosmos can be. In the space of a single season, the Mars approach, the hidden perihelion, the post-perihelion return, we will either close a case or open a new chapter. Which will it be? Keep your eyes on the sky, keep your questions crisp. The universe just sent an envelope. We are opening it together.